Hello, this is Fernando Yepes-Calderon, leader scientist at SVP, and today I'm going to show you the core of the development that we are trying to accomplish. It is related to cancer, early detection of cancer, and we are planning to use artificial intelligence to reach that goal. It is all based in a method that we managed to publish in Taylor and Francis. I'm about to show that, you see, as we are the authors, we have the paper over here. So we are going to see the details on the real paper, not the one online, but in the real one right now. So this is the paper. You can download it from that web page for a price. But as I repeated, as we are the authors, we have it here. So the first thing that we did, we are willing to characterize different shapes because our method is shape-based. And the idea is to find out a mechanism that tells us how rounded are these figures. We are going to use a CT scanner, because these objects are not a live tissue. This is just to capture the shape of the elements. There is one that is very, very rounded over here. And these are the reconstruction of the objects that we have here on top. Okay? This is pretty much the method in flow diagram. I prefer to show you how the method works from here. Here are the images. First step is to create the mask that separates the tumor from the surrounding tissue. And here we have two examples. In this case, this mask is the biggest. You see that the squares are pretty much the same. So we have an equal field of view on the whole tumor. That means that if we see it as a volume, you will see that the volume is like put into a box. And we have this mask. What we are going to do over here, this is a small mask, is that we are going to amplify. For example, we grab this mask, we grab the biggest mask, and we amplify the mask so it becomes as big as this one. We amplify it until the small mask touches the boundaries of the square that contains the biggest mask. And we do that with all the masks in the tumor. With this mask, what we do is to capture the edge. Here is the edge. And then measure the distance from every point in that edge to the center of the field of view. Remember that the field of view is common. So there is only one center of the field of view. So we start measuring that distance to the edging points, and that's the way we open that. It's like a set of points, the distance, you get the distance over here and you create a vector of distances. That vector of distances, if this thing is completely rounded, what is going to happen is that the distance is all the time the same. So you are going to have, instead of having this shape, you're going to have a constant. So you see, what we are doing with this method, and it's very sensible, is to capture the things that are abnormal compared to a perfect circle. Once we have this profile, which is the vector of distances, we apply a filter. That's why you see like a green element with high frequencies, and then the red one that has, it's a filtered version of the first one. And in the red one that is over here, what we do is polynomial approximation until we reach 90%, 95% of similarity. The index of the polynomial gives you an idea of how intricate is the shape of the form that you are analyzing. And here we have a couple of them. For example, you got this form that comes from something like this, the vector of, this is the vector of distances of something like this. It's going to be, the degree of the fitting polynomial is going to be 4. But if you got something like this that comes from something like this shape, the degree of the polynomial is going to be 26. So here, what we have is the representation in a histogrammic signature. The histogrammic works in a way that they say that you find that all the cuts, all the slices on this figure, you're going to have over here in the first beam, the slices that give you a polynomial between 0 and 4, for example. Here between 5 and 9. Here between 10 and 14 and so on. And when I'm talking about those numbers and those ranges is the degree of the polynomial. So for this element, most of the degrees of the polynomial fall in the first bin. And these figures are pretty rounded, but you see how sensible the method is. In the almost perfect circle, you see that it's not perfect because you got a contribution here in a bin that is a high level polynomial. The almost circular things are here in the lower part. And this one that is this one is perfectly rounded. Our method proved to be very sensible. Here we have tumors. Those tumors are very speculated, and you can see the signature, the histogrammic signature. And remember, these here are numbers, see? And the reason why I say that, I clarify that these are numbers, is because this is what we can use in an artificial intelligence. We have translated to numbers something that is qualitative. So we quantify something that is qualitative, and we see the differentiation that there is between neomasses that don't have cancer in the quantification, which is represented by this histogram, and the ones that are we know that they have cancer. So this is what we plan to use in our development, and since the initial test shows a good sensibility, we are pretty sure that we can do it. We are going to use this index to quantify the cancer, and then we are going to use these numbers to teach a machine using as a supervisor factor or feature the histology. And we need data, we need tons of data, we just need to put hands on. Okay, here I'm going to show you the library that supports all this automation, because this works automatically. Okay, this is the code. You see the code grab the images from a path, and we have different methods. We have the different elements. For example, this one, read the file, read the image. And over here, we prepare the data. We find the first point, which is the one in the middle. So we know that it works. I think that will be enough. This is the one that returns the polynomial. And here is, for example, we are very exigent in this example. We define that the comparison is going to be 99% instead of being 95. So now that you know the idea that we have, it is important to mention that we already solved the issue of collecting data. I'm going to show you another video where we work inside hospitals and we can gather information from these highly protected databases in a manner that is HIPAA compliant. And well, the idea is to have a bunch of data, tons of data, in order to accomplish our goal, which is, as I told you, being able to diagnose cancer in an early stage, and with that increase the survival rate. But also we need to keep working, and this device, the one that we are developing, should be inside a hospital. We really work in a platform that allows our code to reside inside the hospitals, and therefore work in the environment where it is supposed to work. So we have this companion video where you can see the core of the system working, and we have other videos because as we have the vehicle that works inside hospitals, and we can connect that with cell phones, and it's a big project. But this one in particular, the one we are presenting to you, is the one that has to do with cancer. Later, we're going to connect this device, the cancer device, with the platform that we have that works with all the pathologies, because the platform is a vehicle for medical data, not only images, a lot of data. So I don't want to extend this video. I invite you to see the other videos that we have for you. Thank you so much, and I'll see you in another opportunity. As I told you, this is Fernando Yepes, leader of SVP. Thank you.